In this lecture we're going to look at the transformation of strain and the use of strain gauges in experimental stress analysis. Previously we looked at the transformation of stress using Moore's circle to find stresses at any orientation from the stress components found at X and Y directions, for example, and we also used Moore's circle to find the principal stresses, the maximum shear stress, and their orientations. We'll use Moore's circle and the transformation equations in a similar way to transform strain. So before we start doing that, let's have a look at what strain is and the definition of strain. You should have seen this before, but let's just quickly look at it again. So in the general state of strain we have three normal strains, as we have three normal stresses. And we also have three shear strains. Normal strain has the symbol epsilon. So these up here, X, Y and Z, to denote the directions of the normal strains. And we also have the shear strains here with the symbol gamma, and also X, Y and Z directions. Actually, I've just noticed here that there's a little bit of an error in the notes. So for the shear strain there should of course be two subscripts there to denote the direction. So we should have gamma XY, gamma YZ and gamma ZX to properly denote those shear strains and their directions. So down here we have the normal strain in the X direction, so we may have just a force pulling in this direction or a stress in this direction to extend that elemental square and elongate it and change its length in the X direction. Similarly in the Y direction we have a normal strain there where the angle between the sides stays at 90 degrees, right, showing that that's a normal strain. In diagram C over here we have the shear strain, and the shear strain is characterized by a change in angle between the sides. So where we had here was originally 90 degrees, that's reduced by some amount, by some angle, and that change in angle between those two sides originally at 90 degrees is the shear strain. So normal and shear strains in X and Y directions, or YZ or ZX directions, can be transformed in the same way as the stress, as I've already mentioned. You can see those strain transformation equations here for you. So there, if you go back and look at the stress transformation equations, you'll see that they have the same form with one small difference, and that difference is here we have the shear strain divided by 2, whereas previously for the stress transformation equations it was just the shear stress, and the normal strain and the normal stress parts of the equation are just the same. So it's just this shear strain divided by 2 that's different in terms of the form of the equation from the stress compared to the strain transformation equations. Okay, so from that those equations we can find the principal strains and the maximum in-plane shear strain using similar equations to what we saw before with the stress, but just with the factor of 2 in there to take into account the difference between the shear strain and the shear stress. So as with the stress, we can plot those equations on a Moore's, and for Moore's circle for strain it looks something like this. We have again the similar issue with whether we have a positive or a negative shear strain that we had with positive and negative shear stresses. One thing that we can say, so over here on this right hand column of this slide we can see that we've got if you've got a positive shear stress, then that results in a positive shear strain, and a negative shear stress results in a negative shear strain. So when we plot Moore's circle, it's the same thing that we did with stress. So here on our horizontal axis we have the normal strain rather than the normal stress, and on the vertical axis we have the shear strain, but it's shear strain divided by 2, whereas with the stress Moore's circle we just had the shear stress. So in plotting Moore's circle for strain, we have again just 2 points, point X and point Y, that correspond to the normal stress in one direction and its associated shear strain divided by 2, and over here we would have the normal strain in the Y direction with its associated shear strain. And as with the Moore's circle for stress, one of the main difficulties is working out whether the shear strain should be plotted below or above the horizontal axis. And various textbooks use different means of explaining this. Some will say you plot positive shear stress down here on this axis, negative shear strain on this axis above, or you can look at the rotation of the element like we've done over here. But the problem with looking at the rotation of the element like we did with the shear stress is that usually when we're dealing with strain, the strain values come from a strain gauge, and all we've got is numbers. We don't actually have an element to look at in order to work out whether the strain is going clockwise or anti-clockwise, and whether we plot it above or below the horizontal axis. But a positive shear strain will be plotted down here below the horizontal axis, and that's what this little negative sign in front of this term here does for us. So whether we're looking at the X point or the Y point, the shear strain is positive for both. It's a positive shear strain. So in order to get this point down below the horizontal axis, we have this minus sign in front. So over here, if I just go and write that in for you, that Y point there would be strain Y, gamma Y, X on 2. Okay, so that's that point there. Right, so we don't have that minus sign in front here. Alright, so having constructed Moore's circle with our strain components, go and calculate the principal strains, maximum shear strains, and so on. So of course, as usual, out here will be the maximum normal strain, here will be the minimum normal strain. If we rotate our Moore's circle so that it's horizontal, then that corresponds to the state of strain where we have only normal strains acting. Okay, so the original strain element just gets bigger or smaller. It doesn't change shape into that diamond shape. Okay, so the angle between the two sides always remains at 90 degrees. Okay, so we can looking at Moore's circle. Along here, the shear strain is 0. And we can also rotate around to the vertical orientation like this to find our maximum shear strain. Okay, always remembering that the Moore's circle for Moore's circle for strain has the shear strain divided by 2. Okay, so looking at our little triangle again, a little right angle triangle in there, we can use that in order to do some trig and calculate our principal stresses. So we'll need the radius of the circle and the center of the circle, and from those two bits of data we can calculate our principal stresses. So we need the average stress and the radius of the circle just from trigonometry, and then of course E1 will be strain average plus R, and so that's E1 there, and that's E2 or E minimum, and E2 will be E strain average minus R. Okay, so moving, this slide here just has a description of what a positive and negative shear stress and strain are. I'm not going to go through that, you can read that for yourself from your notes. So what we're going to look at now is the use of strain gauges to measure strains. So if we want to know what the stress in a component that's already in existence, part of a machine or a structure, and it's experiencing loads, we want to know what the stress is in that component. There's no way to directly measure the stress. We've got to measure or work out the stress indirectly. So one way of doing that is to measure strains and then convert those strains into stresses. So in order to measure strains, we make use of electrical resistance strain gauges such as this. So we can use them singly or in pairs or in fours. But commonly, if we want to find out the general state of stress and we have very little idea of what the directions of the stresses will be, we'll make use of 3 strain gauges arranged in what we call a rosette, looking something like this. There's 3 or 4 different arrangements, but the most common one is this 45-degree strain rosette. So a very useful equation that we have is this general strain transformation equation, which comes from the transformation of strain equations that we looked at previously. So what this equation allows us to do is for any state of strain, so strain in the X, strain in the Y direction, and the shear strain in the X and Y direction, we can use this equation to find the normal strain at any orientation to this x-axis. Okay, so if, for example, we use this strain gauge here, we've got strain in the X here, strain in the Y in this direction, then we can work out the strain at any orientation using this equation here. So that equation is split up into 3. So what we have here is 1, 2, 3 terms in the equation. So if we want to know what the strain in the X, Y and shear strain in the X and Y are, then if we have 3 measurements of strain, we can solve for those 3 unknowns. Okay, so if we have a strain gauge, we measure strain A, we measure strain B, we measure strain C, okay, all at some angle to this x-axis here. So strain A, for example, here, measure that value using the strain gauge, and that gives us an equation with strain in the X, strain in the Y and the shear strain as unknowns, and we know the angle of the strain gauge. Do the same thing with strain gauge B. We measure the strain in this direction, so that gives us a second equation with strain in the X, strain in the Y and the shear strain as unknowns. Measure the strain in the C direction. We know its orientation, theta C, put that into the equation here, and that gives us 3 equations and 3 unknowns, so we can solve for our strain in the X, normal strain in the Y and the shear strain. So if we use a strain gauge rosette like this at 45 degrees between each of the strain gauges, and we align our x-axis, the axis in which we're going to calculate or find out strain in that direction, strain gauge A will give us that strain directly. Okay, so if we put in here theta is 0, so let's in here, if we have theta equals 0, theta equals 0 equals 0 equals 0. Okay, so cos squared or cos theta will be 1. Sine squared or sine theta is 0, so that one drops out. Sine theta is 0, so that drops out. So we can see strain in the A equals strain in the X. So we solve for one of our unknowns straight away. Okay, and that's, I guess, fairly intuitive. If you put a strain gauge in that direction, you're going to measure that strain. You can do the same thing with the strain in the C direction. If that's aligned with the Y axis, then that's at 90 degrees, so cos 90 will be 0, sin 90 will be 1, and that one will be 0 as well. So strain C will give us strain in the Y direction directly. So then we've just got one further equation that we can use to solve for the shear strain. Okay, so having obtained the strains from our strain gauge measurements, what we really want from this is the stresses. So we need to convert those strains into stresses, and the way that we, of course, is via Hooke's law. So for a general triaxial state of stress, the general form of Hooke's law looks like this. Okay, need to note at this point to not simply use strain in the X equals stress X over the Young's modulus. Okay, that form of the equation for Hooke's law is only valid if the stress state is uniaxial. Okay, so be careful that you don't just use this anywhere. Okay, it must be a uniaxial state of stress for that equation to be valid. So in general, we use this generalized Hooke's law, which takes into account the Poisson strain. Okay, so if you stretch something in the X direction, then it's going to get narrower in the Y direction, right, because of that lateral strain. Okay, here we have the Hooke's law for shear stress and strain. With shear stress and strain, we only have this simplified version of the equation. There is no coupling between the shear strain in one plane with shear stress in another plane. Okay, so we don't have to worry about any lateral or out of plane shear strain being developed from a shear stress in another plane, like we do with the generalized Hooke's law for normal stress and strain. Okay, so using those equations, we can then take our measured strains, convert them into strains in X, Y, Z directions, and the shear strains associated, and then we can use the generalized Hooke's law to find our stresses. We can also use this generalized Hooke's law equation in terms of the principal strains and stresses. So for example, we could have strain 1, so for the principal strain. So if we go in here, strain 1, so that will be here the maximum principal stress, stress 2 and stress 3. So we've got the three principal stresses here, strain 2, so principal strain 2, stress 2, stress 1, stress 3, and same thing here, strain 3, stress 3, stress 1, and stress 2. So this becomes useful when we're using our strain gauges to find principal stresses and maximum shear stress later on. So the experimental stress analysis process, we can actually go two pathways to find our principal stresses from the measured strains from strain gauges. Okay, so here we have our measured strains from the strain gauges. We use our transformation of strain equation to find the strain components. So strain X, strain Y, and the shear strain X and Y, for example. Then we can use more circle to go over here to find the principal strains. So strain 1, strain 2, and the maximum shear strain. And then we can use the generalized Hooke's law that we just looked at on the previous slide. Okay, so that's how we would go down to here to get our principal stresses. The other thing we can do is to use to go from our measured strains to strain components, then go down here using the generalized Hooke's law to get the stress components. So here we would have stress in the X, stress Y, and the shear stress XY, and then from there use more circle, like we have previously, to find our principal stresses. So stress 1, stress 2, and the maximum shear stress. Right, so in summary, we want to go from measured strains here to the principal stresses. So we can go via strain transformation to get strain in the X and Y directions, use more circle for strain to find the principal strains, and then use generalized Hooke's law to find the principal stresses. Or we can go from the strain components, use the generalized Hooke's law to get the stress components, and then use more circle as we've done in previous weeks to find the principal stresses. And here, because we want to get stresses from our strains, what I've done here is to rearrange the generalized Hooke's law so that we make, so here's our generalized Hooke's law that I showed you before, in terms of strain equals Young's modulus, stress, and the Poisson's ratio. For a state of plane stress where we have the strain gauges attached to a free surface, then stress in the Z direction will be 0. So a more useful form of these equations is to invert them so that we have the stresses as the subject. So we can calculate our stress in the X from our strain components that we've determined from the measured strains, and we can even go one step further and substitute the strain transformation equation so that we have our measured strains put into into the generalized Hooke's law equation to calculate stresses directly from those measured strains.